So our first session this morning is a bit of an introduction where the aim is to help all of us understand a bit more about this whole thing that's referred to generally as digital disruption and its implications for agriculture. We have three speakers very well qualified to help us, I guess, get a broad understanding of the developments that are occurring and some of the issues. Their CVs are in the program that you have available, so I won't spend a lot of time introducing them and reading those out to you. In the interest of time, I'll go pretty quickly. So our first speaker is Dr. Dennis Buckmaster, who's the Professor of Agricultural and Biological Engineering and Assistant Dean at the College of Agriculture Office of Academic Programs at Purdue University in Indiana in the United States. And Dennis has also been instrumental in the open access agriculture data program or initiative that's been developed in the USA. So to give us his views on these issues, please welcome Dr. Dennis Buckmaster. Thanks, Dennis.
Thank you very much. It really is a very consider it a privilege to be here. I just want to quickly acknowledge that list of names that you see on the screen. This type of effort truly is a team effort, and I'll try to refer to that a little bit later. That list of people there are some electrical and computer engineers, some agricultural and biological engineers, some agronomists, various other types of scientists that we try to collaborate with. And my charge was to talk about digital ag systems in the U.S. and possible lessons for Australia. I hope I keep remembering to say the word lesson through my presentation because hopefully you can learn from some of our mistakes. I do want to just quickly acknowledge that there is a written paper that you'll have access to later. And although my outline is similar to the paper, it's complementary with the E, complementary, not a copy. So the things that I say and show are different than the things that you will read later, although it is the same topical outline. Well, this I borrowed from a fellow from the Netherlands actually drew this diagram, and I put it in there to remind us that, at least in cropping systems, agriculture, whether we're dealing with low-tech or high-tech, we're kind of in the same cycle of look at data, store it, retrieve it, share it if needed, analyze it to make a better decision, and the cycle continues. And sort of the dream is to do that in a high-tech way, in a digital way, with data that seamlessly does that background for us so that we can actually do the farming, do the agricultural decision-making rather than the data manipulations. But that would require that lots of things work together. We have public data sources, research models, and decision aids and tools. We would have private data and inputs. Those things really need to work together to make ag big data really leveraged to improve farmer decisions, advance the research methods, and enable improved policy. But these things working together, that requires solving two challenges, which I will get to. So I really like this quote: the problem well stated is a problem half solved. So we really need to start with what is it that we want to use the digitalization, the data, to solve. Ponder that well enough to design our sensor suites, our data manipulation and processing, so that we can indeed solve it. So I would like to just point out that in agriculture, although there's big data in lots of realms, agriculture is a little bit different because in our science, in our enterprise, there is a lot of biology, chemistry, and physics that explains things. So whether we have big data, truly big data, or not big data, sometimes it doesn't really matter. But models need lots of data, sensors don't. And the other key difference between agriculture and other businesses that deal with data is our farms are small. They don't have a dedicated information technology department. So that's why the people like us need to make these things work a little more seamlessly. One of my very good colleagues at Purdue is Aaron Alt. He's also a full-time farmer. He spent 4 minutes one day writing down as fast as he could what are all the decisions that he would like to be able to use data to improve these decisions. So he wrote this list in 4 minutes. Each one of those, to a scientist, could be a research project. I suppose some of those could launch a research program over many, many years. But these are the questions that farmers want to answer now, for this year, for next year. And data should contribute to the answers. So let's think just specifically, since I'm from the Midwestern of the U.S., just thinking about corn. These are the data layers about corn. The soil, the topography, you can see the list there. Lots of different layers. And the source of those elements of data are very different. The aggregation level is different. But if I want to completely tell the story of corn, I need to know each of those things. So one of the words that we've been throwing around for a few years now is metadata. It's data about the data. Probably to the data scientist, metadata is usually, was the sensor calibrated, what's the format of the data file, some things like that. But I like to focus on the bottom part of that. It's the descriptive information about the context, the quality, the condition, and the characteristics of the data. So let's go back to the corn situation. If I'm trying to analyze corn yield, then it's not only the population of the corn, it's the variation in the population, the standard deviation of my plants per hectare, because that affects yield. It's not just did I chisel plow the field, it is what was the soil moisture when I chisel plowed the field, because for some soils that would be very important. It's not just how much water did I get over the year, it's the water stress during ear filling, which is very critical. So this is the whole context, the backstory, if you will, about the corn production. If I want to mine corn data, truly mine it, then I would need to know all of that. So that's sort of my introduction. A little bit about the digital agro evolution, at least in the US. There are lots of digital agricultural products. I refer to some of those in the written paper, not all of them, but a few of them. But I'd just like to point out that many of those, and a couple will be represented here this week, came from companies that deal with seeds and supplies. Some of them come from companies that have their roots in machinery. Some had accounting and management as their core competency in the business. And then there is an influx of the IT people, information technology. That is their core competency, and they're moving into agriculture. So it's kind of been an evolution of where do these come from, and just like everywhere, it's all about mergers and acquisitions, it seems. Well, I would like us to think about the 3 tenses of data. In the bottom left is the logistics of today. Top, it's evaluating the past actions. But in the right bottom, it's the forecasting and planning for tomorrow. Which of those 3 do you suppose need the best quality data? Which of those 3 might encourage a person to have the best quality data? That's where we'll go. Well, here are some of the players, not all of the players, but I would just like to point out that some of these players probably do a better job of dealing with the logistics of today, logistics being what, where, when, and how. Some of these would have a stronger competency in the planning for tomorrow, and some of these would have their best competency in looking to the past to see effects and impacts. But what we really want to do, use data for, is all 3. I hope, anyway. So, one lesson. Despite the marketing, the complex fundament, despite the marketing, there are lots of questions in ag data still. Because if you believe the marketers, they would say we have it all solved. Well, it's not quite true. And there's just more happening every day. So I have 2 near-term challenges that need attention. And the first one I want to talk about is interoperability. It is the ability to exchange and make use of information. So I have a little story. I'll try to get through this very quickly. I could spend probably 30 minutes just on this one thing. But Frank, the farmer, and Andy, the agronomist. Frank wants Andy to give him a prescription map of what seed variety to put on which soil, at what population, and how to fertilize it, and those sorts of things. In order to get there, they start with the conversation. First thing Andy is going to want is, well, what was your yield map last year? So Frank will have to deal with original equipment manufacturer A to get the data out of the combine through the cloud and then pass it off to Andy. Well, Andy probably wants last year's data and the year before, and perhaps that was with a different combine, different manufacturer. Maybe it was custom harvested. So he's dealing with different clouds, different files. Of course, some of the data that Andy would need are just on his computer. It's the soil test and other information about the farm. I could go slowly, but I won't. But there are several other elements of custom applied fertilizer, the seed descriptions from last year. What happens is Frank finds himself dealing with data when he would rather just be farming. But in order for this to work, Andy needs that data. So that's today. It's just truly not very interoperable data. Data in different clouds, different systems, incompatible software, also at different aggregation levels and such. But all we really want is to get that prescription map sent to Frank's planter. So one of our efforts at Purdue has been this. The Open Ag Data Alliance is dealing with interoperability by creating APIs that allow these clouds to communicate. So essentially with a federated identity, Frank can provide access to Andy to acquire that data, and Frank now removes himself from manually copying from a disk, sending it by email. It's all secure access through the cloud. So that's the more dreaming, less nightmare version that we're shooting for. So back to this, can these things work together? In order for public and private data and research models to work together, the data has to be interoperable. Okay, related to the interoperability, we might have multiple devices. These could belong to the same person or different people, but we're going to get some data that might be aerial imagery. There might be soil data. In our case, it's publicly available now through several apps. There's the weather data, field boundaries, planting data. That probably is private, so I would own it and provide access to those that need it. And then I might use just a generic cloud storage like Google Drive, Dropbox, Box, or other things where I would store data and make it available. What I want to point out here is that the most likely scenario is not only multiple devices on multiple software platforms, but it's also multiple clouds. Lots of the industry, when they draw these diagrams, they always have their cloud in the middle. I don't think it's really going to play out because unless, perhaps, and I'm not trying to encourage one company over another, but unless something like climate and John Deere and Syngenta merged, there isn't going to be one cloud because they each have a need for a cloud for some of their data. So this interoperability is confounded by that. So the next little quick topic I'd like to cover is just the privacy, which happens through good security and the provenance. And there is a range here from the bottom, which would be raw data, very specific, very detailed, but very much very private, all the way up to the top, which would be publicly available, discoverable, mineable data. As we would move from the bottom to the top, there are transformations of trust. And I consider this analogous to taxes. Hopefully, what is your tax day here? 1st of July. Okay, so you're thinking about it probably now, aren't you? Ours are due in April, and I'm done thinking about that. But anyway, I did see H&R Block is here, and that's who I use in the U.S. It's analogous to taxes. There is a legitimate reason for the government to know some of my personal information. They don't need to know all of my personal information, but they need to know some of it. How do I do my taxes? Well, in my case, I do it myself. But often, we have a trusted advisor, the accountant, who we delivered a box of paper. We say, here. And they transform that into the report that goes to the government. So there is a trust between me and the accountant to sort through that, deal with it in the proper way, and report the aggregation level that is needed to the government. In a likewise way, there are going to be transformations of trust from raw data to some company's cloud that might make the data more useful broadly. Some of it will be statistics data reporting to the government or regulatory perhaps, or even at the top level, my contribution to the betterment of agriculture. I might aggregate some of my data and report it just for the betterment. But that requires transformations of trust, which would require someone to be that trustworthy entity, that company, that business. All right, let's get to the second near-term challenge needing attention, and I call it, in one word, quality. Quality has several different dimensions to it, and the one I would want to focus on is context. If I may slow down just to make sure we get it. Context is the circumstances that form the setting for an event, statement, or an idea, and in terms of which it can be fully understood and assessed. Back to my corn story of a little while ago. If I had corn data, but I didn't have context, then what good is it? I need for it to be fully understood and assessed. So I have a couple examples. This is one from one of my graduate students, Elizabeth Hawkins. This is a yield map for the same field. One of these three is correct. Two of them are not correct. And the only difference is a software setting on the combine yield monitor software, which is called flow delay. And what it does is it just shifts the data from where it was collected to where it was relevant in its georeference. That same field has several different soil types, has quite a lot of field elevation change. Because of the soil types and elevation changes, her approach to this, to mining this data, was to identify integrity zones. Inside those integrity zones, she has reasonably high confidence that the data is sufficiently valid. Let me put it the other way because I think it's easier to understand. Outside of those integrity zones, there is something fishy that makes her wonder about the integrity of the data. In this case, for the most part, it's either soil type transition or combine yield monitor function. So data outside those integrity zones is, frankly, questionable. Would you want to use questionable data to make decisions for the future? Probably not. So a good place to start with data quality is to simply erase and not use the data that you consider questionable. So here was the result. If she took in that third column field mean raw, that's the yield that the monitor tells you. But if you clean and prorate, by clean I just mean using those integrity zones, then you get a much more accurate picture of the truth. Another example of quality would be this one. This is the fuel data from a controller area network on a tractor that was pulling a manure spreader. And probably to the casual user, you look at that graph and you'd say, that looks like a bunch of nonsense, just data on a graph. That's interesting. But once you know the context, it becomes very rich. So here is the context. The cycle here was load the manure spreader, go to the field, unload the manure spreader, go back to the lot, load it, go to the field, unload it, go to the lot, et cetera, et cetera. Once you know that, you'll see that along the bottom, the fuel consumption is very steady. That is when the tractor is sitting still, waiting for the manure to get in the spreader. When you go to the field and unload, You can predict fuel consumption very accurately. The point is, context is everything. That graph, without context, is useless. With context, is very useful. So, agriculture really is a logistics business, getting things in the right place at the right time, and it's very much about that. One of the reasons we found in the US that this interoperability hiccup hinders the adoption of digitalization. It's the lack of the return on the investment. The payback is just not seen. That hinders adoption. So one way to solve that is to design software that will improve the logistics of today. Then the users will see the immediate feedback. Rather than just promise the dream of better decisions in the future, let's promise I can help you do better tomorrow. And by doing that, we'll probably get better data. So as one example, this is one, it's a software hardware interface that we designed there at Purdue. It's just simply called the Manure app. And with the Manure app, I put that little tag on my manure spreader. I carry my cell phone, and my job is to spread manure. I don't have to keep any records. We call this autogenic because it's automatically generating the data. And what I would get by not doing anything is automatically a map of where did I spread the manure, and by load, where did it go, where did it come from. So this is an example of eliminate the human, let the machine collect better data. Let's see, I skipped one. Yeah, so let's go here. So some of the analytics needs that I think, and hopefully you can learn some lessons from this. One thing we have not solved is data architectures that work together. We do need quality assessment algorithms. Some algorithm that can analyze a set of data and ascertain the quality level of that data based on its context and the data. One of the things we need to do is simply identify the data needs, and that gets back to the problem statement. And then I would also like to propose that we need refined models. If we're going to truly capitalize on the benefit of data, in the end, and you'll see this in my written paper, you're going to use data to make a better model, to make a better decision. So we need to refine those models. Well, I'm at an educational institution, and I would like to think that the foundational experience of learning helps people, students, build confidence and critical thinking. It helps them enable lifelong continuance, and I think it may be time that we rethink what we used to think of as an agricultural education. You'll now see in that green box, software coding. Maybe we need some agricultural disciplines to know how to deal with software in addition to their science or their engineering or their economics. As I reflect on our work over the past few years, it's the importance of teams that probably is my biggest lesson that I have learned. And that is to know your place and have your sense of the other person's place. And I tried to address this a little better in the written paper, but I am an engineer, an agricultural engineer. Machinery is my space. Software writing, not so much, but I could do it. Agronomy and soil science and plant production, I understand it, but I'm not the expert. To do this requires a team where each team member appreciates the value of the other person to the team. And there does need to be some shared terminology that an electrical engineer understands a little bit of agronomy, and the agronomist understands a little bit of software engineering, but they don't need to be an expert, but they need to appreciate it. So there's common terminology, the culture of collaboration, and I believe that's probably born in the educational experience. It comes early for them to realize this is larger than me. It's going to take a team. What is my place in that team? Okay, I'll just be quiet for a moment and let you read that quote. Now notice the date, almost 140 years ago. Big data before data was cool. All right, so here's my last slide, I think. The lessons. One is don't fall for all the marketing hype. We do need to improve our education and training. We're trying to do that better. True solutions will require integrated teams, and hopefully that educational experience leads to that. We do need to aim to improve data quality, because out of improved data quality, that's where we will get our better answers. Aim to improve the interoperability. And then lastly, but maybe even though I didn't comment on it yet, maybe this is the most important one, and that is to cultivate the open source community. Although I knew the term, until I was surrounded by it, I don't think I appreciated the open source community. And open source is, you should just Google it if it's new to you, but it's where the code is freely given away. Not the data, but the code. And so it's a grassroots effort to make things work better. And here's what I found in the US. Although lots of companies and enterprises are they're for the open source community, they're not positioned to contribute to it because they don't have the in-house expertise to do it. So it takes some cultivation to generate that open source community. If we can chat perhaps later over break or something about some examples of how open source solve many problems that we deal with in our outside of agriculture life, but it's not been applied to agriculture just yet. So I think my time is probably about right there. So Mick, give control back to you.